Dr. Gold in the lab, Twitch stream glowing, formulas flashing, minds wide, knowledge flowing, equations on the board, numbers never sleep, teaching math and physics while them haters count sheep. Actual education, tune in and get schooled, flipping textbooks, breaking all the rules, from Newton to Einstein, concepts elevate. Keep the stream, it's the key to our fate. Dr. Gold dropping gems, knowledge raining down, actual education making scholars all around. Perpendicular minds, angles sharp as ice, maths and physics, yeah, the future's real nice. Got the Pythagorean triangles about to flex, quantum theories on deck, breaking all the specs, relativity theories, worlds getting small, grasp the universal laws, standing tall. From the atom to the cosmos, we rolling deep, grazing up the stars, no time to sleep. Black holes and supernovas, concepts we unfold, brain power heavy, yeah, that's Dr. Gold. Dr. Gold dropping gems, knowledge raining down, actual education making scholars all around. Perpendicular minds, angles sharp as ice, maths and physics, yeah, the future's real nice.
What's up, everybody? Special Thursday stream for our students who are taking AP Physics 1 exam tomorrow. 6-1 review. Let me start this on Discord real quick. There we are. What's up, Sensation? Dun, dun, dun. I wonder if I can project my screen. You know what? The bitrate gods have not gotten mad at us yet. And actually, I did something you suggested, Sensation. I reset my internet router, and like, yeah, magically, I suddenly get more like bitrate. Like what? I was like, let me try this. Let me try doing this.
That's not what I said.
I think you did say. I mean, earlier today you told me to like fix all my OBS things, but again, I don't think it's a computational problem. I think it is literally just a bandwidth issue. But for whatever reason, if I don't know.
We know it's not a bandwidth issue because it's only Twitch.
That is true. It is only Twitch. Okay, so I'm gonna monitor it, but whatever. I think it's working for now. Y'all tell me on Twitch if things start like going haywire.
Yeah, I don't think it's a bandwidth issue. I don't think it's a computational issue. I think that Twitch is very finite in its usage, and so the more shit you turn off, the more it might work.
Okay.
And that's kind of what I'm hoping for.
We got too many flashy things going on the stream today. That's what we're saying.
Well, no, because if you don't tell it to turn it off after you've stopped using it, it continues to be used.
Sure, but I would hope that it would only broadcast what like I'm telling OBS to broadcast. It shouldn't be broadcasting background things, right? Maybe?
I'm not sure.
We don't know. Anyways, one thing we do know is we're here to help you guys with AP Physics 1. This is pretty late, honestly, in the AP schedule. This is like week 2, I think. Wow, thanks for the follow. When will the thing start? It's going to start soon, momentarily. I'm going to give people like 5-10 minutes to like load in. Because I technically told his name is Dan. Dan's a great guy. His name's Dan Burns. He, I think he does a lot. He's been on, I think, the board for like creating AP Physics questions in the past. He's a really big physics high school educator, and he reached out to us actually about 3 years ago, asking to use a platform that I support and work with to host like an AP Physics review course. And if you want to know what that course is, here let's go to it. I gotta remember what the website is. It's actual.education / and I think it was AP Physics 1 2025. Is that the website? Oh, I got it right. Oh wait, no, I didn't. Uh-oh. Oh man, I could have sworn it was AP Physics 1. There we go. This is it. Yes. So here's the. Oh, why is that not linking to the right thing on YouTube? 1 second. AP1 is algebra mechanics. It is. 1 sec. There we go. Okay. So yeah, this was the website that Dan sent out to everyone. Oh wait, this is the old website. I think it's like -2025. There, this is it. Here we go. Okay, this is it. All right, yeah. So, what we have is, so yeah, here, I'll put this in the chat for everyone if you don't know about it already and you want like some fast like study questions to go through. It's pretty cool. Where's my chat? Here's my YouTube chat. I didn't know. Yeah, so this isn't one of my regular streams. This is a special AP Physics 1 stream. But I decided I'm going to do it on TikTok. On Twitch as well. Okay. 2 Dr. Golds. Yeah, that's me down there as well. So that's us when we're doing AP Physics. But anyways, if you go to this website here, Kudu, you can create an account for free. You add this course, and if you ever want to, you just click here, and it'll get you into the course. So, oh, do I have to add this course to myself? Really? Okay, whatever. Here it is. AP Physics 1. Okay. So this has all the different chapters that are going to be covered on the exam, as well as some good like practice questions, some homework questions that we've taken from Dan, who's written a bunch of AP Physics questions before in the past. And so here's like a whole selection of practice things, and you have unlimited checks. You can check it as much as you want to make sure you get the right answer. So that's a free course if you want to get some extra practice in. We also added in a bunch because new for this year is fluids. They took fluids from AP Physics 2 and they put it on AP Physics 1. Quite rude of them, honestly. But that's what we got to deal with. So, so we added a bunch of stuff here about fluids and a ton of practice questions that you can go through here as well if you want. So it's all there. And then additionally, there's some cool, important equations to memorize.
Nice.
Here. This is from another friend we worked with in the past, Jonathan from Flipping Physics. We worked with him actually on this course a couple years ago. He does his own thing now with Ultimate Review Packet, which is cool. It's a very useful thing, and it's not that expensive. I think he only charges like $20-30 for it. But he had like some equation sheets here that were useful to memorize. To be fair, fluids is part of the first semester physics. It is. I teach physics at UCLA, and for our first year class, we don't do fluids. We do fluids in like it's the second semester, or yeah, it's the second semester. It's physics 5B. And then yeah, so while all you guys are here, and what we're gonna go through here is the live stream review. So here was the link and everything, so that you guys could have seen it. But yeah, what we're going to do today is I'm going to go through the FRQ section of last year's AP Physics 1 exam and kind of work through and show like some tricks and tips and what I would do to solve these types of questions and to make sure you can do it in the fastest amount of time and also the most accurately. So this is for AP Physics 1 specifically, but so after I go through the FRQ, I'll open like kind of open office hours. And if you have any questions about AP Physics 2 topics, you can also just ask those after we go through the FRQ. So it'll take me probably about an hour and a half to go through the FRQ. After that, I'll leave the stream open. And if you want to ask any questions about AP Physics 2, AP Physics C, I don't care. I'm more than happy to go over it. So you should see that there is a chat in YouTube. And then there's also a chat in TikTok. Jeff says, what is physics? You know what physics is, Jeff. So yeah, any questions, please feel free, drop things in the chat. we'll be happy to help you out and get you some help. Okay. Let me see. Do I think I got everything? Shandrick's saying, are AP classes equal to your first year of college classes? Yes, usually. You get credit for at least your first year of college. Is it as hard? I tend to think actually college classes are harder than AP classes because they go more in depth and there's more time. Whereas AP, they're really just trying to get you, I would say like a medium level of understanding of whatever the course is, but you get credit for a full level. So if you're trying to be a physics major or you're trying to like really do physics, I would recommend actually retaking one of the physics classes when you get into college, because AP physics won't necessarily, it'll do a lot of good, like it'll help you out a lot, but it won't give you like a complete understanding. It's better to, this is what I did. So I came in with 60 credit hours in college from all my AP exams. I took so many AP exams, and that was great. Saved a ton of money. But I ended up retaking E&M my first year of college because they wouldn't let me take the next level physics until my math had caught up. And I'd already tested out of calculus and everything, but I had to take like vector calculus before they would let me take waves in physics. So rather than not do any physics, I retook E&M my first semester. And honestly, like I learned a lot running through it the second time. So little tips and tricks. Okay, cool. All right. That being said, let's get started and help you guys out with AP Physics 1. All right. All right. Welcome everyone. Office Hours. My name's Dr. Gold. This is Actual Education. I'm joined by my wonderful host here, Sensation Black. What's up, Sensation?
Get off my lawn.
Get off my lawn, kids. I love that movie. I think it's great. One sec. I gotta re-log in on this, actually. One sec. There we go. Okay, cool.
I can't really do his voice, though. It's quite difficult.
Well, it changes. Are you talking about, what? Not Chuck Norris. What's his name again?
Chuck Norris. Clint Eastwood.
Clint Eastwood. Good old Clint. Yeah.
Kind of like really sort of tight-jawed.
It's like raspy.
What is with all this bro shit anyway?
Dude, I love that film. Gran Torino, right? Is that what we're talking about? Gran Torino?
Yeah, I never understood why he pointed his finger at the gangsters.
Oh, and then he gets shot at the end. Spoiler.
Yeah.
Yeah. Sad. Okay, let's see. Question 1 here. It says, a block of mass M is released from rest at point A at a height 6r above the horizontal. After being released, the block slides down a track as shown. When released from point A, the block does not lose contact with the track at any point. Points B and C are located at the highest points of their respective circular loops with both radius r. All frictional forces are negligible. Love it when friction is negligible. Helps us out. Okay. This was all, you don't even answer anything on this first page. They're just giving you all the details for what you need to do next. So then they say, continue with your response here on question 1. So here we go. Math is really hard. Yeah, it's okay. We're here to make it a little bit easier for you guys. Okay. So it says diagram A shows an energy bar chart representing the gravitational potential and gravitational potential energy UG and the kinetic energy of the block at point A when the block is released from rest at a height 6r. Okay. So this happens a lot of times. Things are released from rest here, which means that the velocity at A is equal to 0, which you should know just right off the bat before I even see what the question's asking me. I know this is something to do with energy. And I know that kinetic energy is equal to 1/2, in this case, mVA squared. So since this is 0, the kinetic energy here is going to be equal to 0 at point A. And we do see this here in the graph, right? So we see that the kinetic energy is 0, and it has a very high amount of potential energy because it's very high up. And I'm curious, actually, is this thing equal to 6? Is this 6 bars? 1, 2, 3, 4, 5, 6. Wow. They were even nice for us that way. Because we should also know, right, that the potential energy for something is equal to mgh. And in this case, this is equal to mg, and the height is now equal to 6r. Oh, thanks for the follower, Ezra. Love it. Thanks, bro. 6r. Okay.
TikTok?
I don't want to tempt my bandwidth yet, so I might do it later during like the halfway point. Yeah. But yeah. Okay. Yeah, we got 50 viewers on YouTube. Just no one's talking on the chat yet. That's okay. I see your chat at least. All right, this is cool. Cause see how this is 6 MGR, and I see that this is like 6 different things, like 1, 2, 3, 4, 5, 6. That tells me this must be like 6 MGR, and then this must be like 1 MGR. Cool. All right,
Just
it says.
Remind me, what's big R?
Big R is the radius. In this case, they're defining R as the radius of these loop-de-loops. Okay.
Yeah, that makes sense.
And they're using that length to then describe the height of this thing at the beginning as being 6 times. So you can actually think about this, right? It's the same thing if we wanted to like stack a couple of these circles on top of each other. It would be like this, right? Do you see how like... Do you see that sensation?
Just aren't these questions a bit weird though? Because I mean, in every test I've ever seen at any level, there's still sort of units involved, like real.
Yeah, no, this is all units. In terms of variables. Yeah, physics likes to do this. People get scared. They're like, "Oh no, where are my numbers?" But physics likes to do things just in terms of variables, because it's useful to see trends. It's useful to see how things cancel out. And then also, it makes grading easier, because now they're not chasing down, like, numbers. They're just looking for letters. They're just like, oh, do you have the right letters? Okay. So it says for diagram B, draw something that represents UG and KE when it's located at point B, which is 2R above the horizontal. So that's right. That's right here. Okay. So our roller coaster, which is... this thing, right? This thing is going to fall down, and then it's going to come all the way back up, and it's going to stop right here at the top. Okay? And so we want to talk about what the energy is here. Now, the potential energy will have changed, because we are no longer located 6R up. Instead, we are now located R plus R. We are located at a height of 2R. So here we're going to say mu G is going to equal to M G, and now this is going to be 2 times R. Okay? Or if we want to like simplify this, this is 2 mgr. Isn't it also 2R on its way down? Yeah, right here, it's also going to be at a height of 2R. It's a good point to recognize. They only want us to talk about point B right now. And the key thing here... so if we know the mu G has now dropped to 2 mgr, that's going to be like this. Okay. And then they want to talk about... Now we got to talk about the kinetic energy. Here's the key thing here. The total energy at any of these points, like A, point B, or point C, needs to be the same. And because we're only dealing with things that are moving and things that have height, we only need to consider potential energy and kinetic energy. There's no springs, so I don't need to worry about spring energy, and nothing is like rolling. Like we're not talking about the wheels, so I don't have to think about rotational kinetic energy. So the total energy here at point A was equal to the kinetic energy plus the potential energy, and that was equal to 6 mgr. Now the total energy here needs to also be equal to 6 mgr. The potential is 2 of those mgrs. So that means the kinetic energy has to be equal to 4 mgr. Because I need the total of these things to add up to 6 mgr. Because total energy here has to equal total energy here. So, if I know this one is 2, and then the next one is 4, so now we can go 1, 2, 3, 4. So that's going to give me this. And there we go. That's the kinetic energy for at diagram B. And let's check. I do have the answer key, so we can check to make sure we have the right thing. And yes. So the key thing is they wanted something where they added up to 6. Let's get rid of that. And this was the correct answer they wanted. Nice. So yay. 2 points down. Love it. That's easy. Okay. Any questions about that before I go forward? Again, if you ever have any questions about like what's happening here, please type in the chat and we'll go through. Okay, cool. All right, now let's do the next part of the question, which is part B. So now they say, starting with conservation of energy, derive an expression for the speed of the block at point B. Express your answer in terms of R, physical constants as appropriate, and so they say begin by writing the fundamental physics principle or an equation. So the fundamental physics principle here is that at point A and then at point B, that the total energy, so we say Ke plus mu g here must equal Ke plus mu g here. And what we know, right, is that at point A, when this thing was starting here at rest, oh, I flipped the colors. One second. That's gonna annoy me. Let me flip the colors. Sorry. Green is A, red is B. Let me just do that. I understand that you don't get like colored pencils and stuff on your exam, but to just make it easier for you guys to see it on the stream. Although I don't know, apparently like the AP exam is now all on a computer. Like you don't even take like test booklets anymore. I was like, what? That's super weird. Okay. So at the beginning, at point A, it's starting at rest. And if something's at rest, that means 1/2 mva squared. This is going to go away and be 0. Okay, so this goes away. And then this is equal to 6 mgr. Okay. Then at the end, or at point B, where we're looking at, we're going to have 1/2 mvb squared plus the potential energy here, which is now 2 mgr. Okay. So now all that's left to do is to solve for VB. That's what they want, right? They want the speed of the block at point B. Okay, so we can just move some stuff around. So first thing you should notice here, and this happens a lot. This is why we do things in terms of variables, is because it's really cool. Do you see how there's an M, an M, and an M here? That means I can just divide both sides by M and just cancel out the M's. So this goes away, this goes away, this goes away. You wouldn't have been able to see that if you plugged in numbers for mass, because the mass times 6 here would do something, the mass times 1/2 here would become something else, and the mass times 2 here would become another number. And so it would be harder to see that, oh, I can just cancel all the masses. Like the mass does not matter for this. But okay. So now I can move this over. So 6 GRs minus 2 GRs. So we're going to do minus 2 GR. Minus 2 GR. That's going to get me 4 GR is equal to 1/2 VB squared. And then I'm going to multiply both sides by 2. Right? Get rid of this. And then I'm going to take the square root. And I'm going to get the square root of 8 GR is equal to VB. I think for style points, you can write the square root of 8 as 2 square root of 2. Equal to VB. I believe that's all you need. Let's check the answer key. Very cool. So yeah, this was the answer that they got, which, yes, square root of 8 GR was valid. And then key thing here, right? Energy before equals energy afterwards. We wrote that, right? And then we described what the different parts of the energy were. And then we solved. So cool. That's another 2 points. Down on the board. Pretty easy. Okay. Before we move into the next part, I'm going to take a little second to ask, does anyone have any questions on how we did this with conservation of energy? Because now what we're going to get into is like rotational dynamics. They're gonna step it up a little bit. Okay. Let me make sure. Yeah, and YouTube is working. Okay. We have lots of views, Sensation, dude. 77 views on YouTube. Hell yeah, that's dope. Okay.
Don't forget to like and subscribe.
Don't forget to like and subscribe, guys. Yeah, do it. It'll make Sensation so happy if you like and subscribe. Look at him.
I will lick my ass like a cat. Like behind the ear and everything.
Yeah. Bernadine says my AP test is tomorrow. Okay, good luck. Donut Master Jam says, couldn't you have just said K equals KE and said that you put earlier with KE equals 4 mg? Interesting. So, yeah, you are right that when we were at this part here, Donut Master Jim, that I already knew that, right, this energy has to equal this energy. Sorry, that the total energy here has to equal the total energy here. So if I got 2 blocks here, then I got to have 4 here to have a total of 6. I think because the question says derive an expression, and it says starting with conservation of energy. Oh, here's the other key thing here you need to look at, Donut Master. It said begin your derivation by writing a fundamental physics principle.
Nice.
Okay. So the fundamental physics principle you have to write, which I know it's like you're repeating yourself, is you have to say that the total energy here equals the total energy here. So you're right. You could have, if they just strictly wanted you to get the answer, like what is kinetic energy? Sorry, what is the velocity? Totally. You could just say, oh, well, this has to be 4 mgr, and then I just set it equal to 1/2 mv squared. Yeah, but the key thing here is that, yeah, they want you to write it again. It's annoying, I get it, but it's a good way to double check yourself, right? You know, maybe you had made like a mistake here, like counting lines. I don't know. I've problems sometimes. But okay, but yeah, good, valid points. Okay, it says on the following dot that represents the block, draw and label the forces that are, and not the components. So they just want the raw forces that are exerted on the block the instant the block slides through point C. Each force must be represented by a distinct arrow. Okay, so here, I'm going to pull this down so I can see what's happening again. This is the advantage of having copy-paste abilities on a stream.
Oh, no. Somebody mentioned the JEE. Take a drink.
The JEE. Take a drink. Yeah, should we have like a drink every time someone mentions JEE? That's the Indian exam that they all take to escape poverty, right? And like go to college.
And it's like mentally difficult, yeah.
It's like really difficult. Like even I would like screw up at it. Anyways, okay. Umang says in college I have Schrodinger time equation. We have to derivative it. You mean take the derivative of it or derive it? I can do it. I'm doing AP Physics 1 today, but if you want to stick around after the stream, I'm free to. I'll do some quantum with you guys. Yes, these are the practice problems for the AP Test FRQ. This is from the AP released FRQ from 2024. And so what I'm doing is I'm speed running, or well, it's not speed running because I'm not trying to do it as fast as possible, but I'm going through the whole thing so that you guys can see the thought process of how to solve these types of questions and, you know, ask any other conceptual things that may not make sense.
That's not water, it's gold.
drink gold. Okay, all right, so point C. So they want to know what are the forces that are acting here. So this is cool. So at the top of this roller coaster, all right, you're always going to have, oh, that's a jug of water. Jesus, Sensation, that's a big jug of water. Yeah, the Sensation has the biggest jug of water. Okay. We always have the force of gravity. Gravity is always acting on stuff, and it's always pulling stuff down. Gravity pulls things down. Okay. In addition, okay, because, let me think. I wonder if I'm allowed to do normal force here. I wonder how in depth they want me to go. Let me check real quick. Yes, they do want to. Okay, cool. Okay. So the block. This is kind of tricky how they wrote this because you just see a circle. So here's what's really happening. Okay. The block is right here. Okay. And it is connected to the surface of the track. Okay. Now, anytime anything is touching a surface, touching a track or whatnot, that object is going to experience a normal force. from the surface it's resting on. So in this case, the block will have a normal force pointing down from it being resting on the track. Cool. And then also anything that is on Earth here has the force of gravity pulling down. Okay. So, when they say to draw the forces here, we need to draw a couple forces. So I need to draw force of gravity, which is pulling down, and then I also need to draw the normal force. And you don't know how much the normal force is because that depends on how fast it's going, and we'll go into why that is. So I don't think it necessarily matters the lengths of these yet, because we have to do a little bit of math here. Good. So there is no such thing as a centrifugal force.
Surprise, motherfucker.
Centrifugal forces are fake. It's a centripetal force. There is a centripetal force. Well, there are a series of forces that provide for a centripetal acceleration. That's what I like to say. Technically, this and this are centripetal forces. But anyways, let's see what the response was. So their example answer was this. So good. Yeah, we drew about the same thing. And yes, you just had to label FNFG. That's great. You could have labeled it as W. You could have labeled it as force of Earth on the block. What's up, hooligan? Good to see you, dude. And then here's this, any non-zero magnitude, right? So you could have had this one be shorter than this one, or longer, as long as it had a length. We're going to go into, like, I think in the next part, like, what the length is. But so far, always draw the force of gravity acting on things, and anytime you have something that is on a surface, okay, you need to draw the normal force of the surface acting on that object. Does that make sense to everyone? It's tricky. I would have maybe almost gotten the normal force thing wrong there, because they said at point C, but they didn't really, like, show that the block was there. What is a stress tensor, and what do its values mean? That's an engineering term, and that has to do more with forces acting in opposite, like, directions on an object. That's like a material science question. Oh wait, that's all we had to do for question 1? Man, they're not even gonna make us derive. This is really cool. You can actually derive the speed of this thing and the normal force if you do a little bit more work, but apparently we didn't need to do that for this. I thought that would be the next thing. Although yes, they said questions 1, 4, and 5 are short, so these should have only required 13 minutes each. And then questions 2 and 3 coming up require 25 minutes each. Yes, exactly. V squared over R. I'm just going to show like a little hint, little teaser to this. Because this thing is moving around in a circle, it has some velocity in this direction. And because it has a velocity in that direction, it's going to have a centripetal acceleration that points inwards towards the center. And what you would say is that, so the sum of the forces, which is minus Fn minus Fg, has to be equal to the mass times the acceleration. But the acceleration is the centripetal acceleration, which is negative because it points down. And so this would end up being negative mv squared over r. So there's a way that you could solve for the normal force here. And in order to get the velocity here, you would also use your same conservation of energy, right? The total energy here has to equal the total energy here, which has to equal the total energy here. Is there a pseudo force being applied? Yeah, technically. So if you're the block, you want to keep flying in this direction. Like, you don't want to stay on the track. So what happens is the track pushes down on you with this normal force in order to keep you going in a circular motion. So the normal force that you feel acting on you is kind of like, that's a centripetal force, but the force of you wanting to go to like exit, like you feel like you're being pushed against this track, that's called a centrifugal force. Centrifugal force, and that's a fake force. It's fictitious. But okay. All right, so they didn't want you to go too far in depth there, but just as a little like teaser for like what can come up, that's another example. Let's put this back.
Wait, what did you say was the fictional force?
Centrifugal forces. So as a little like, yeah, here I'll
centrifugal.
So the centripetal.
Right.
This is real. And then there's centrifugal, which we say centrifugal. And this is fake.
Well, you're doing it wrong, but yeah.
What do you mean I'm doing it wrong? Centrifugal is fake.
Oh, just the way you and I pronounce things.
Oh,
sometimes you get them right, sometimes I get them right.
Oh, okay. Yeah. This has to do, the technical definition of this is the force that is felt from your inertial reference frame changing. And I know that's like a bunch of big, like scary math physics terms. But basically what it means is that if you, for instance, are moving around, let's say, for instance, you're taking a tight turn, right, in a car. When you take a tight turn, do you ever notice that you feel like you're being, like, pushed out? Like, you're getting pushed out to, like, the edge of your car, like, on your seat, right? If I'm, like, driving and I take a hard left turn, my body wants to keep going in this direction, okay? But friction from the tires, from me steering inwards, is forcing me to go this way. So what you feel is like your body wants to go this way, and so this is called like a centrifugal force.
Nice.
There's like this fake force that wants to push you in this direction, but you're instead forced to move around in a circle. This stuff fucked my brain up in AP Physics. Yeah, I agree. What's up,
I've got a
Sensation?
better example for you, actually.
You got a better example. What is it?
At these fairgrounds that pop up all over the place.
Ooh,
You've
yes.
got them, we've got them. So there was a machine, they pretty much banned it universally now, but there was loads of mats around the outside of a circle.
Okay.
It would spin. And then
Yes.
it would spin faster and faster and faster, and eventually it would start turning on its side. Now, the centripetal forces would basically make it so you could stand sideways and look down at the ground.
Oh my god. Oh, that's crazy.
Yeah, and so if it slowed down too quickly, it'd fall off. People
Yeah.
died, so.
No, that's a very cool question. That's a cool, that's a carnival ride that they do. They sometimes, here, before we do this question, I'll just a little, physics is fun.
You weren't strapped in. It was just pads on the.
No. And that's totally possible. So they would sometimes have this, where they would have a person just chilling here, on something here that has like a wall, right? And then they would spin this around, right? Okay. And then eventually, once it's spinning fast enough, they would drop the floor out here. So, and you would be staring straight down into nothing.
The thing would turn 90 degrees on its side.
Oh, okay. And then you would just be like looking like straight down.
Well, because then you'd stand on the wall.
Uh-huh.
Or sit and look down, and then it was mental.
This person looks like his name is Bob. Yeah, we'll call him Bob. Yeah, it turns out that if this thing spins around fast enough, there's a centripetal acceleration inwards, which means that there has to be like a normal force between you and the wall, and that provides friction that prevents you from like falling down. It's pretty cool. The gyroscope, yes. Yeah, I know what you're talking about. Like, so that's actually conservation of angular momentum is what that is. Yeah, where he has the wheel and he's spinning the wheel and then he like starts moving the wheel and it like fights you. Yeah. That's a pretty cool one. Yeah. That has to do with conservation of angular momentum. But all right, let's go
to experiments about conservation of momentum in space when they were spinning something.
Yeah.
I can't remember now.
There's a bunch of these.
It was something
like if you spin something, you end up
Oh wait, if you spin something in space, it tries to continuously orient itself, and so every few spins it would flip around.
Oh, interesting.
Am I right?
I think so. Things that spin in one direction usually want to stay spinning in that direction, and if you fight it, it'll try to reorient itself to the way it was spinning. It's the same thing with like linear momentum. Like if you have an object that's moving at a certain direction, it wants to keep going in that direction. So if like you, so with things that are rotating, they want to keep rotating on a certain axis, unless you try to move that axis, and then that requires a force, like it fights it. In the same way that like if a train is moving with a certain velocity, right? In order to make the train move somewhere else, you have to apply a force. You have to fight it. It's the same thing with rotating things. Yeah. It's a cool experiment. Okay, but let's see this one. It says, a student hangs a spring of unknown spring constant K vertically by attaching one end to a stand, as shown. At the other end of the spring has a small loop, which cylinders can be hung. Okay, cool. The student... Oh, this is one of these lab questions. I hate these. Because, I don't know, like, some kids, like, don't have access to a lab. I'm from Los Angeles, and I know a lot of students here lost... Well, first of all, lost their high school in the big fire up in the Palisades. And so they haven't been able to do any of these labs. But, okay. Lost it again. Come back. There we go. Okay. The student only has access to cylinders, a stopwatch, and a scale. Cool. Design an experiment the student could use to determine the spring constant K of the spring. In the following table, list the quantities that you would measure. Define a symbol to represent each quantity. Describe the overall procedure. Provide enough details so that a student could replicate the experiment. And then make a diagram. Okay. So this is where, like, to do these types of questions, you have to kind of remember what you did in lab. But I understand that, like, not everyone had access to a lab. You should have, but my suggestion for students here, like, for instance, the ones that lost their homes in the fire and lost their school, is to go onto YouTube and see people doing these experiments. Okay, cool. So, quantity to be measured. So, we have a bunch of unknown masses, and we have a scale. That's cool. So, I think one quantity I would love to measure here would be the mass of cylinder. Cylinder, whatever. We call it, like, M, right? And I think I'd want a couple masses, actually. So here, so let me explain, like, what we're going to do in general, because what are we trying to determine? Determine the spring constant. So here, this is the physics behind what you're going to do. So you're going to take, for instance, you know that this is some distance, let's call this, like, x naught, okay? Actually, let me change the color of this. This is equal to x naught. It's this distance. And then what we're going to do is we're going to apply a bunch of different masses. So, for instance, this could be... Ciao. What's up, dude? Let's say this is like mass 1. And then... let's put another mass 2. And then basically, what we should know, right, is if we were to draw force diagrams on this, right, this would have mg, so m1g pulling down, and then it would have k, and then we're going to say this is like times x1 pulling up, because this is the force of the spring, where x1 refers to this distance. So this distance here is x1, because it's the amount that the spring stretches from its equilibrium position. And then here for mass 2, you would have kx2 and then m2g. Take notes, guys. Yeah, take some notes. So this distance would be equal to x2. And so here's the cool thing, is that if this thing is hanging, right, then it must be at equilibrium. And so the acceleration of it should be 0. So what we could end up doing here is be like, okay, well, kx1 minus m1g has to be equal to 0, because there's no acceleration if it's at equilibrium. And then also kx2 minus m2g is equal to 0. And now, if you measure different stretching distances, and you also measure the different masses, you can set up a systems of equations here to solve for what K is. Well. So, you don't even need to... you don't even need to use different masses. I mean, you could, for instance, like, not measure this. And then if you measure this and this, you're still okay. But, all right. So they said quantity to be measured. So I would say massive cylinders. Let's see. Bernadine says, can you also use what? Ooh, I like that one. That's actually a cool one. You are actually, that is correct. I didn't even think about that. Oh, so here's a good question. Yeah, wait. Did we... Oh, so actually, we didn't even get a measuring tape for this. So actually, you are more correct, Bernadine. Now that I look at the answers, I originally assumed that we at least had a fucking measuring tape for this, but we don't. So this is out the window. We actually can't do this. My bad. I thought we at least had a measuring tape. We don't. Bernadine is correct. If I don't have a measuring tape, now what I have to do is I have to look at the period of oscillations. Yeah, totally right. So, yeah, what was the question? So here. The question was, we're designing an experiment in order to determine what the spring constant is of an unknown spring, okay? We're trying to figure out what K is. Given that we have a bunch of different masses and we have a stopwatch. And so what Bernadine brought up, which is a really good point, is that if, for instance, you hang one of these masses by the spring. See, I thought we at least would get like a ruler, but like I guess not. If you hang one of these things by the spring, one of these masses by the spring, and you pull it down and you let go of it, it's gonna oscillate, okay? And that natural oscillation, which is omega, is equal to the square root of k over m. This is the angular frequency at which something will oscillate. Now, so yeah, we only get time. So we have to compare. Yeah, it is simple harmonic motion, good. So we have to compare. You could do the number of oscillations in a certain amount of time, or you could calculate the amount of time for a single oscillation. Either works. So this is the one I always remember. Like omega is equal to square over k over m, which is also equal to I think it's square root of L over G. This is for like pendulums. These are just useful things to know, right? Or no, sorry, it's G over L. My bad. G over L. This is pendulum. I always got to remember, like, wait, so if length goes up, well, it should take more time, which means the angular frequency should go down. And then this is for a spring. And these are all examples of simple harmonic motion. And since omega is equal to 2 pi f, and f is equal to 1 over the period, you can then say that omega is equal to 2 pi over the period, or period is equal to 2 pi over omega, which dividing by omega, which is square root of k over m, is the same thing as multiplying by square root of m over k. So this is equal to 2 pi square root of m over k. Okay. So that's what we need to do. So we need to measure the mass of cylinders, and then the other thing we need to measure is the, I don't know, the period of oscillations. Or here's what we could do. We could say the time for 10 oscillations. Okay. And then that symbol would be T. Okay. So then what I would do is, like, I would weigh mass 1, attach to spring, pull down, release. Use stopwatch to record time for 10 oscillations. Because then what I'm going to do is I'm going to take that time and just divide it by 10. This is just it's just kind of a way to do like multiple trials in like a single thing. Because if you tried to like record like a single oscillation, there's gonna be a lot of error in between doing that, right?
What is shm?
Shm is simple harmonic motion.
Okay.
Or Swedish House Mafia, depending which one you like. Okay.
Flap hose mama.
Okay. And yes, that's kind of what they had so far. Okay. I hope they ask us for the math for doing this. Okay, here they go. This is what they want. This is what they want. This is the money here. They say indicate the quantities that could be plotted to produce a linear graph whose slope can be used to determine the spring constant K. Very cool. So let's look at, for instance, what we have here, right? Which is that period. So the time being recorded is equal to 2 pi square root of K over M. So here, period is equal to 2 pi square root of K. And then I'm going to put the M below there as well. Sorry, M over K, not K over M. K over M is always omega. I always want to do things in terms of omega. Okay, so here's the cool thing. So if I want a linear graph, right? A linear graph needs to be in this form. You have to have that y is equal to like some slope and then times some x value, which we call x, okay? So right off the bat, I see, for instance, that I could call this, for instance, my y, right? Let's just call this y. So I'm going to say I'm going to plot on my vertical axis t, which is the the time for an oscillations, the time for one oscillation. So then maybe in the instructions here, I would say like then divide by 10. Just so they know that we're not doing it for all 10. Okay, so if that's y, then the thing I'm looking for is going to be k, but the thing I'm varying, so we're measuring time, but the thing we're changing, so we're not changing the spring constant because it's the same spring. We are changing the mass. So this thing is going to be the mass. Okay? So on the horizontal axis, I would put the square root of the mass. Okay? Then the slope is whatever's left here, which is this. So the slope is equal to 2 pi over the square root of k. So they ask, how would you analyze the slope to get k? Okay. Well, once I have the slope from, again, graphing period versus the square root of m, okay? Once I have, this, I can solve for k. And so what I'm going to do is I'm going to move this over here and move this over here. So I'm going to say the square root of k is equal to 2 pi over the slope. And then I'm going to square both sides. And that's going to get me that k is equal to 4 pi squared over the slope squared. So that's how we would determine the spring constant. I would measure the period for a bunch of different masses, right? That would give me a bunch of like data points like this. I would fit a line to it. And if the line for the graph of period versus the square root of m has this slope, 2 pi over the square root of k, And then solving for k, I'm just like swapping these and then squaring it. I would say, oh, well, k is now 4 pi squared divided by my slope squared. That's kind of a lengthy one. But it's totally valid. And yeah, here they said you could have done that. So we could have done t versus the square root of m. That was a valid answer. Cool. And then right. So then what you get for your k being as a part of your slope depends on what you graphed. So if we did t versus the square root of m, which is what I did, then your slope would have been equal to this. So k would have been equal to 4 pi squared over the slope squared. Yay, what's up, Zach? It's going good. We're through the second question out of, I think, 5. It apparently takes them an hour. They give them an hour and a half to do this thing. We're probably going to take 2 or 3 hours because I'm explaining every step. But yeah, it's going well. Okay. And it's actually kind of cool because on their grading rubric, they're like, you could have done any of these. Like, it's kind of like a choose your own adventure thing.
I have one of those books.
You have the choose your own adventure?
A couple actually. One's a Mario one, one's a Zelda one.
Here, let me delete this page. I had one for like Star Wars. An hour and a half for this one question. Well, I mean, no, you get an hour and a half for all the questions. You get an hour and a half for all 5. You get 25 minutes for this question. I'm just saying, on the stream, we've been on for like an hour and a half because I don't know, we're taking our time explaining things. But this is kind of cool. So they said, here, you could have done any of these possible, like this versus this, this versus this, but then here's all the different different ways you'd have to manipulate the slope to get k. Some of these are just swapped order. Yeah, they are, right? Yeah, m versus t squared and t squared versus m. And yeah, you should notice that then how you solve for k is just a reciprocal of it, yeah. Square root of m versus t versus the square root of m. Yeah. I mean, also, this is kind of the same thing, right? Right? T versus the square root of m is kind of the same thing as t squared versus m. It's just hilarious, all the different answer choices you could have put for this. But these are all valid. Okay. Anyways. Okay, cool. So I think we're done with that question. Yeah, dude, this is the rubric. This is the rubric, man. Okay. Oh, wait. Now they say in a different experiment. Bro, what? How is this still part of question 2? It's a completely different experiment. Oh, okay. I guess this is all like, just like students are being experimental or something. Okay, it says, in a different experiment, a student attaches one end of a spring to a force sensor that is attached to a wall. The other end is attached to a cart. This has a mass equal to 0.25 kilograms. The student places a motion detector to the right of the cart and pulls the cart to the right a small distance so that the spring is stretched and then releases and it oscillates. Oh, and then they're going to give us this. They're going to give us some graphs. So here's the graphs of the velocity and the force. Cool, they're out of phase with each other. That's pretty cool. It should kind of make sense. This also has to do with like F equals kx type stuff. So again, if you have your car here, right, and we pull our car out and then we let go of it, it's going to oscillate like this. And one thing we should remember from springs, right, is that when the spring is furthest away, that's when it has the most amount of force, because force is equal to kx, right? X is the distance from equilibrium. But also at the ends, that's where the velocity is going to be equal to 0, because the velocity is changing from being positive to negative. So it makes sense here, for instance, right, that the velocity is 0 when the force is maximum, right? See, at 2 seconds, the velocity is 0, but also at 2 seconds, the force is maximum. Okay, but what's the question they're asking here? Okay, here they go. All right, they say, using the data in the velocity time graph, calculate the change in kinetic energy of the cart from 0.5 to 2 seconds. Show your steps and substitutions. Okay, so the kinetic energy of the cart only depends on the speed of the cart. There is going to be potential energy stored in the spring. But, okay, so going from 0.5 to 2, right? So we can say that change in kinetic energy is going to equal to 1/2 m, and then that's going to be v final squared minus v initial squared. So just 1/2 mv squared final minus 1/2 mv squared initial. So this is going to be equal to 1/2. The mass of this cart we said was 0.25. The final velocity here is 0. And then the initial velocity was 0.3. So minus 0.3 squared. Okay, cool. I wonder, do I have to give an exact value for that, or are they cool with like decimals and shit? Let's check the answer key. What do they want? Oh, they do want a number. Okay, so in this case, we have to pull out a calculator. So we're going to do 0.5. How'd you get? Okay, good. No, that's good. Good point here. Okay. So it says calculate the change in the kinetic energy. Okay. Very good point, Furious Panda. So let's remember what kinetic energy is. So kinetic energy is equal to 1/2 mv squared. So change in kinetic energy is going to equal kinetic energy final minus kinetic energy initial. And so this is going to be 1/2 mv final squared minus 1/2 mv initial squared. And what we should notice here, right, is that I could pull a 1/2 m out of both things here. And that's going to end up getting me 1/2 m, and then it's going to be v final squared minus v initial squared. So that's what we get for that. Does that make sense, Furious Panda? I realize, yeah, I skipped a couple steps there. Cool. Crazy Matt says, I'm guessing this is for Physics 1. I just took Physics C, E, and M, and I got destroyed. Oh, no. I'm so sorry. Yeah, this is for Physics 1. They have AP Physics 1. The exam's tomorrow. So I'm just going through the FRQ from last year. But...
Oh, no.
Oh, no.
Oh, no. Oh, no.
E and M is tricky. I liked E and M. E and M was my favorite part of physics. I loved E and M. Circuits. Yeah. Drink more water.
TikTok. TikTok.
Oh, yeah. I'll do it when we start doing the open questions. I'll do TikTok.
Could you
That's a good idea.
Could you edit it as AP? You know, when you go live on TikTok?
Yeah.
Could you give it a talk there?
Wow. Okay, anyways, I need numbers for this. Sorry, my bad. Where are my numbers? Where's my calculator?
100 people on YouTube. Please
we love that.
Like and subscribe and join the Discord and do all that fun stuff.
Yeah, help us out. We're a nonprofit. We help students like you guys out with math and science. And not just physics. I mean, I teach everything at this point. Chemistry, statistics, calculus. My PhD is just in physics, so that's why I'm qualified or whatever. Okay.
And I'm supposed to teach everything you don't, but then no one ever asks those questions. So.
They don't really, yeah. You don't need help. Okay, so we got that the change in kinetic energy was this, minus 0.0113, and then joules. You got to be important to put joules. Right, and that was the same thing that they did. If we look at their example response. You missed half of Maxwell's equations from track season since I'm a... Oh, that's cool. You're a state athlete. That's dope.
That's dope.
What do you run? I used to do cross country. And my fastest mile time, which I know is not very fast, but it was fast for me. I did a 5:20 once. I broke 6. I was so happy with that. And they did add fluids to Physics 1. They did. You learned Maxwell's equations.
The most I've ever run is to the Alicante.
The most you've run is what, Sensation? What's the most you've ever run?
The furthest I've ever run is to the Alicante.
To the a la carte. To what? It's called the tuck shop, right? In the airplane, it's called the tuck shop.
The trolley.
Yeah, the trolley. My mom would call it the tuck shop. Says, "Oh, go to the tuck shop." Is that a thing?
That's interesting. That's a school thing.
The tuck shop. I don't know what the word means.
Tuck shop's a snack shop in schools.
Oh, my mom would call it like the snack shop on the airplane, I guess. I don't know. Fascinating. Okay, it says use the data in the force time graph. Estimate the change in the momentum of the cart from 0.5 to 2.5. Explain how you arrived at this. You do the pole vault. That's sick, dude. Oh, also, I'm from Texas. I live in Los Angeles, but I'm from Houston. I'm actually flying to Austin on Friday. I gotta go. My buddy's turning 35, and he rented a lake house on Canyon Lake, and so I gotta go say hi to him. So I will be back in Texas briefly, shortly. Okay, change of momentum. This is a cool thing. This has to do with impulse. Impulse. Okay, so what we learn, guys, from impulse, which is written as J, that's equal to m delta v, which is equal to also f delta t. So force times change in time. And this right here, m delta v, this is also referred to as like the change in momentum. And if you want to see why that is, I can show you. It's actually pretty cool. So let's remember that momentum, P. This is linear momentum. Is equal to mv. Okay? So if I want the change in momentum, which is delta P, that's mv like initial, or mv final, sorry, minus mv initial. And if the m stays the same, which I hope it does, that's just m v final minus v initial, which is the same thing as m delta v. And so that's change in momentum. That's where this comes from. Devil says, I also want to help people with math, physics, and mechanics. How did you start? I started by tutoring. I tutored for very low amounts of money at first. You can also volunteer to tutor. I'm sure there are places around that are looking for tutors. That's how I started. And then I formed a nonprofit because I wanted to teach more people, and grants and I don't know, donations, all that stuff. But hopefully expanding. So my big goal for like what we do here is to eventually have enough funding and whatnot to host a bunch of other people that can also teach physics and stuff. We already have a pretty good department just amongst friends, not officially related with my nonprofit, but we have a really good group of math streamers on Twitch. So if you're watching us on Twitch, I'll put the math streamers here, but there's an awesome group of people on Twitch who love to stream free help in math, and you could certainly just start streaming yourself and people would come ask for help. Yeah. Oh yeah, I'm subscribing for math. Yeah, please. Yeah. I stream 3 times a week, free math help, and then when I'm not streaming math help, there's a calendar, which I don't know if your teacher sent this to you, but this is the calendar for like all the streaming that happens amongst us. What's up, Don? We got a raid from Don. Thanks for the raid, Don. Good to see you, Femvox. But this is the calendar for everybody else who streams, not everybody, but the people who decide to put their schedule up, who streams math and science. So Zach is a friend of ours, and he does math. He's a PhD in math, and he does math help in the mornings, and then he does stuff on Saturday. Thanks. Yeah, thanks. Cool shirt. So here, I'll put that link there. Yeah, that's the link for the schedule. We're Actual Education, so this is office hours. I'm doing a bonus stream right now for AP Physics 1. But if you need help in other math things, Zach also streams in the mornings and on Saturday. And I mean, even here, Talos teaches an exploratory calc class on Sundays. Yeah. You're gold square today. Yeah. Do you make videos or just live stream? I do both. So, just quick little detour before we... So, if you're seeing us on YouTube, then you obviously know... you probably found me from YouTube Shorts, or you found me because one of your teachers told you that I was doing a live stream. But we do live streaming, and then we also do tutorial videos on YouTube, and then we also do them on TikTok as well. TikTok is where like I really get to, I don't know, help out Gen Z, because all of Gen Z is on TikTok. So we have a bunch of videos on, you know, for instance, is finding images with lenses and mirrors. I hate lenses and mirrors, but we make videos for it. Yes, and there's the Discord. If you want to join the Discord and get more help throughout your academic career, please do. We help you out. Okay. All right, cool. Let me go back to this question real quick. I've done a video on law of sines and law of cosines for sure. So you can also suggest questions, and I make videos on them if there's enough. I do a lot of grade 11 stuff. Yeah. Go check it out. If you go to the YouTube here, I say the YouTubes. One sec. Where's my channel? And you go to playlists, and then you go to math in 60 seconds. Here are all of the videos I've made on like little math tutorial things. And so there's probably something in there for you that you will learn. Lots of calculus. But there you go. That's that. Okay. Yes, for those that are visiting us from Twitch, welcome guys. We're doing a special AP Physics 1 review because all of these high school students have the AP Physics 1 exam tomorrow. And so I'm going through the actual exam from the previous year, and we're showing some tips and tricks on like how to solve it. Okay, so going back into this. So it says, estimate the change in momentum from 0.5 to 2.5 seconds. Explain how you arranged it. Okay, so change in momentum, delta P, is equal to F delta T. Okay. There's a calculus way to do this, but algebra AP Physics 1 doesn't use calculus, so we have to use like baby math. Grade 10 math exam. We'll suggest it. Yeah, suggested exam, dude. I'll do it. And we're going from 0.5 to 2.5. Okay. Oh, this is very cool actually. So they want from here to here. Okay. So if we want the change in momentum, I want the average force. This is also the average force being applied times the change in the time. Here's the cool thing. As you go from 0.5 to 2.5, if you were to look at what the average force is, the average force is 0. Do you see here, right? The average going from here to here, this averages out to 0. So it turns out that the change in momentum is 0. There is no change in momentum. Which seems weird. But also you can kind of see it from the velocity graph here, right? So momentum, right, is equal to mv. Here, the velocity is 0.3. Here, the velocity is also 0.3. So the momentum does not change. So a couple ways you could say this. You could say average force is equal to 0. Say F average equals 0. I could also say the area of F delta T is equal to 0, because this is negative area and then this is positive area, and so as you go from here to here, you're going to get a total area of 0. The fancy way, which I don't think they want you to do, is to do this. You do F dot dt from 0.5 to 2.5 is equal to 0. And that's equal to change in momentum. So, yeah, that's what I would say. I'd say the average force is 0. And let's see what they wanted answer choice-wise from that. Have you ever made content on how to use Desmos for the new hybrid test? I think it's super useful considering the regression lines you can create. I have not. That's a really good suggestion, Crazy Matt. Again, I'm used to like taking exams with pen and paper and like, you know, maybe like one of these graphing calculators. but you are right that the SAT even, you get to use Desmos now, which is insane because there's so many hacks you can use with Desmos to like solve things really quickly. So that's a really good idea. I definitely should like get up with the times and start making videos on that. No, I love the suggestions. Please feel free if you ever want to like DM me or talk more, just join the Discord or whatever. And I'm Dr. Gold. You can just send me a DM. Okay, so here they said for indicating the change in momentum is 0. That's cool. For indicating the area represents a change in momentum, and then the area under the curve is also 0. That's also what we said here. So this is also okay. Yeah. Oh, cool. You've co-authored a Desmos course. Yeah, I would love that. I'd love to get your opinion on that. Okay, and then part 3. Yeah, well, Desmos is just like free TI-84 calculator, basically, with a little bit more modernized stuff. They said, does the data from the velocity time graph confirm your estimation? Well, it does, because remember from here, we said, oh, here, that equals the same MV over here. So P1 equals P2, so the change in P is 0. So I would say like, yes, like momentum at 0.5 is equal to the momentum at 2.5. So change in P is equal to 0. Cool. I think that's all you had to say. Nice. Okay, cool. We're done with 2 questions. Congratulations, guys. We got 3 more to go. 3 more of these physics questions to go. What time are we at on the stream? Hour 16? Okay, not bad. Okay. Oh, this is a statics question. Engineers love these. This is also apparently a 25-minute question. Okay. We love statics. Yes. Engineers love statics. Okay. The reason why it's called statics is because things are not moving, aka they are static. So here they say the left end of a beam of mass M. Okay, so this has mass M. We should remember that. And length L. Okay, on one end of the string, a negligible. Wait. One end of the string. Oh, the string has negligible mass. The other end is attached to the wall. The beam is horizontal. The hinge exerts a force on the beam of magnitude FH, and the angle between the beam and the string is θ1. The following rectangle represents the beam. Draw and label all the forces exerted on the beam. This is definitely the monster. Yeah, Femvox loves this. Yeah, right? Okay. So here's a key thing. Because this beam has mass to it, okay, it's going to have a force of gravity. And the force of gravity always acts at the center of mass of an object, which can be kind of thought of as the balance point. So I know there's going to be a force of gravity here, and that distance it's going to be located is going to be L over 2. So let's try and draw some things real quick. So I know for sure we have the force of gravity, and then that this is located a distance L over 2. I know I'm also going to have the tension in the rope or the string, which is pulling up on the beam at a certain angle. So here we're also going to have θ1, and this is going to be like force of the string, which I'm also just going to call T. And then the last thing is that there is also the hinge. This is always kind of a weird one. People are like, wait a minute. What do you mean the hinge is exerting force? It's just a fucking pivot point, right? It's like, no, it does. Because this beam is being pulled into the hinge. And by Newton's third law, with equal and opposite forces, if this is getting pulled in this way, the hinge has to push back. So it turns out we're also going to have a force from the hinge that is acting, okay? But let me think here. I believe the hinge is also going to be pushing up on this a little bit. Because right here, this would love to fall down. But it doesn't. So I believe the force of the hinge is going to be to the right and going to be up. I might be wrong on that, but okay. I'm going to say there's also the force of the hinge. Oh, the hinge can support both horizontal and vertical components of force. Okay, good. Okay, so we are going to draw it as diagonal. We don't know what the components are yet. I guess that depends on this and this, right? Because I would imagine if you have enough of this fighting this, then you don't need any of this. But then also, this has to then fight this. Yeah, okay. We're going to get to it. Okay, let's see. I think that's all they wanted to, right? All the forces? Okay, let's see what the example response was. Aha! It was diagonally up. You're right, Fembox. So, turns out, yes, this is what they wanted. Which is pretty close to what we got. Interesting they didn't mark the L over 2. I would have marked that. I just feel like that's useful information. Okay. Okay, let's keep moving forward. See what they're going to ask next. Uh-oh. They made things weird. Okay, now things are going to change. So now they say the string is then attached lower on the wall. Okay, so the string goes down lower, and the beam remains horizontal as shown. The angle between the beam is now theta 2. The dashed line represents the string from 1. The magnitude of the tension in the spring is Ft1. The magnitude of the tension of the spring in figure 2 is Ft2. Indicate how Ft1 and Ft2 change. Oh, interesting. Okay, well, let's think about the forces and what changes, right? So, this is going to stay the same. Gravitational force doesn't care about the rope. Gravitational force always points down. What's interesting here is now you're going to have less tension in the rope pulling you up because you're at a lower angle. So if we look at like components wise, right? So when we were in situation 1, we had all of this amount pulling it up. Now in situation 2, however, when the rope has been like dropped, okay, now only a very low amount of it is going to go. This is a tricky question in this direction, right? Lot smaller amount. So I believe the tension is going to have to be greater. And they want us to do qualitative things. Okay, so yeah, I agree that FT2 should be bigger than FT1. That's what I thought. Because you need more force here because less of it is going to get put in the upwards direction. If you draw the tension and joint forces on FG, you see that the tension vector on 2 is bigger. Oh, ooh. Oh, we could also talk about torque. You are totally right. Right, okay. So here's kind of the cool thing. I like talking about it. You're very right. Okay. So in order for this thing to be at equilibrium, you also need the sum of the torques to equal to 0. And so here, if it's rotating about this point, so let's say it's rotating, right? Okay. Then the only torques that contribute is this torque from the force of gravity pulling it this way. And then, that's a very good point, Fembox. And then this torque from this force pulling it up, okay? We already said that if this is at a low angle, then the component of this tension force, which is perpendicular to the radius, which is the force you care about when you're calculating torque, this is low. But if we look at, for instance, when it's here, right, that's much bigger. The component-wise. So you don't need as much here to balance out the torque from here. Okay. That's what I would say. And I like that. That's the justification they put on as well. So they say in order for the beam to remain horizontal, the torque exerted by the string must remain the same for all angles. Yes. When the angle decreases, the perpendicular component of the tension remains the same. Therefore, the tension of the string is greater for a smaller angle. Uh-huh. Here's what they're saying, right? So this perpendicular component, which we call like F perp, that's going to be equal to T sine theta, right? Because this is sine theta, and you want the opposite part of the triangle. And so as the angle decreases, the tension is going to need to increase in order to give you the same perpendicular force, to get you the same torque. So that's why tension 2 is bigger. Does that make sense to everyone? That's a tricky thing. It's a really tricky thing with the arrows and stuff. Because I understand that you're seeing that the green arrow is getting less, and you're probably like, wait a minute, isn't there less force like being applied? And it's like, yes, less of the tension is being applied in the up direction, so you need more tension to make up for the gravity. Your F perp has to equal 1/2 of Fg, no matter whether the string is attached at 1 or 2. So at 45 degrees, it'll change again. Correct. Yeah. Does that make sense, Axolotl? Yeah, Fembox has some good things here. So maybe it might be easier if I drew it out like, let me draw this out like this way. Okay, so this is the rotation point, right? So you always, let's use the right colors for things. So you always have the force of gravity, and that's acting at a distance L over 2. And then you're going to have this tension in the rope. And then this is going to be... This is helping you for tomorrow's test? Good. I'm glad, dude. That's the whole point. Yay. Knowledge. Okay. Okay, so this right here, right? This is like what we call like F perp. Okay. And so, if we do the sum of the torques, so you have this one pulling down. Down is negative torque. Or, sorry, clockwise is negative torque, not just down. So this is negative Fg times L over 2. And then this one's pulling up. And so that's going to be plus F perp times L. Because this is located at a whole distance L. Okay? But F perp is equal to T sine theta 1. Okay? And then we need the sum of the torques to equal 0. So 0 is equal to negative Fg L over 2 plus the tension in the rope. Today's stream is just for AP Physics 1, but we stream 3 other days out of the week and we do everything. So today's just a special one for AP Physics 1. So it's inversely proportional to the angle. Yeah. What's up?
Gold.
What's up?
Whenever someone types like that, you have to say it exactly as it is written. If they want to take the piss with the English language, so should you.
Okay, so watch. L goes away. L goes away. So and then if you move this over, right, you get Fg over 2 is equal to T sine theta, right? So it is inversely proportional. This is for AP Physics 1, which they have their exam tomorrow. So the tension is equal to Fg over 2, and then it's 1 over sine theta, right? So it is inversely proportional to the angle. Because as theta gets bigger, tension's going to get smaller. And then as tension gets smaller, T gets bigger. Yeah. That's kind of cool how that works out. Thanks for the torque recommendation, guys. That was a really good one. Oh, which I think we just solved part C. Yeah, we just did it. This will happen sometimes when you do these questions. So it says, starting with Newton's second law in rotational form, derive an expression for the magnitude of the tension in the string, m theta. So we just did it here, literally. We just did this part of the question. So what we did is, we showed that, okay, torque here and torque here have to cancel each other out, equal to 0. And then we solved for T, which was the tension. And so we got tension is Fg over 2, 1 over sine theta, which, nice, is the right answer. That's what we got. Wow, look at that. Love it when it works out. So great. Yes, even Elon's happy for us. Okay. Let's do part D. Is your derived equation consistent with your justification in part B? Explain your reasoning. Well, yes, right? So we can say yes. UCLA, so this is AP Physics, FemVox coming up. UCLA finals are in 2 weeks. I'm giving out another midterm to my students next Wednesday, though. Because as theta goes up, sine of theta goes up, and FT goes down. And vice versa. Cool. Okay, what's the last thing they wanted? Okay, last thing for this part of the question, and then we just have 2 more questions left. Okay. It says the string is cut and the beam begins to rotate about the hinge with negligible friction. On the following axis, sketch the angular speed of the beam as a function of time for the time interval while the beam falls, but before the beam becomes vertical. Oh. Okay. It's kind of cool. I wonder how we're supposed to do this. We'll find out. Okay. Okay, so what they're saying is okay, can this move, please? Oh man. There we go. They're saying that we cut the string here. And then something happens to it. It one second, let me get it like kind of full here. They say that this, actually, no, I need this as a line. One second. Line, very thick. Okay. They're saying that once this falls, this is going to, like, fall this way. Okay. And they want us to talk about what's happening to the angular speed here, omega. Okay. Here's the important thing to realize, okay? So, when this thing is cut, when there's no more string attached to it, right? That means there's no more tension from the string. There's only going to be one real force that's providing torque, and that's going to be the force of gravity, right? So the force of gravity is going to be pushing straight down, which is equal to mg, and that's going to be located at a distance L over 2. Exactly, axolotl, yeah. So that's going to provide a torque, okay, which is going to be equal to I, which you should know it for this. This, I think, is technically 1/12. Is it 1/12? No, I think it's 1/3. This is 1/3 ml squared times alpha. This is I times alpha. Yeah. Zongju, if you need help with AP Physics, we're going through the exam right now. Otherwise, if you stick around, I'll have like open office hour questions afterwards. So in like another hour or so. Okay. So, and then right, omega is equal to omega naught plus alpha t. Oh, but here's the interesting thing. Oh man, this is weird. It's 1/3 because you take the left point, not the middle, right? Yeah. The middle point, if it's rotating around this axis, is 1/12. Because it's rotating around this axis, it's 1/3. Yes, the issue here is my alpha's going to change. Wow, that's tricky. I think I'm probably overthinking this one. There's probably an easier way to do this. But, yeah, so here's the issue. Is that once it's like descended like this far, okay? Now gravity still points down, okay? But not all of it points in the perpendicular direction. Yes, this is where it's weird. So now right? This is now some angle theta. And so what you say is that, oh, well now torque is equal to the same I, whatever it is. But, wait, one second, sorry. So torque equals I alpha, which is also equal to, now it's going to be mg sine theta. Because it's the amount of this torque, amount of this gravitational force that's perpendicular to this, which is now less. So the acceleration is going to decrease, right? Because eventually this thing's going to like come to here. And now gravity is pointing this way. And now theta is like really small. And so now like not much of this at all is pointing perpendicular to the radius. I can help with trig too. That's cool. What do you prefer, online coaching or offline coaching? I mean, I like both. I think online's easier. I mean, we have 105 people on YouTube right now. I can't teach to 105 people in person. It just doesn't work. Okay, so torque is going to decrease, alpha is going to decrease. So instead of this thing just following a nice line, which would have been this, right? If alpha was constant, then as time increases, omega would have gone up at the same rate. Alpha is going to decrease. So instead of it going straight like this, it needs to like go up at a decreasing rate. So I believe it's going to do something like this. It's going to curve. You can do it with Lagrangian mechanics? Oh my god. Oh my god, no, dude, what? That's too much. I can't do Lagrangian mechanics. It's like taking an acetylene torch to like light a cigarette. Like, don't do that. Or don't smoke cigarettes anyways, but you know. Yeah, anyways. I used Hamiltonian mechanics. But this is AP Physics 1. You're not supposed to use Hamiltonian mechanics. You know. Okay, I think it curves down. Okay, and they do draw it. Here's what they had for their answer. Look at this. Wow. Okay, it looks the same. They don't provide any explanation for it, though. That's so interesting. They really should have. So this would have been if alpha was constant. And this is alpha decreasing because torque is decreasing. And the reason why torque is decreasing is that because as this object rotates, down, the angle between gravity and the plank is decreasing. So the torque is decreasing. So alpha's decreasing. It's cool. Thanks, Fembox. Yeah, nice solution. Yeah. I mean, yeah, their solution's fucking trash, dude. What? Like, they just drew the graph. Excuse me? Can't just do that. That's what?
Oh no!
No, Coral. Coral. Okay. Any questions about that one before I move forward? Abdullah says, can you teach integration using the residue theorem? That's complex analysis, right? I mean, I probably could. I haven't done it in a while. Anything's possible, but not during this stream. I'm strictly doing AP Physics 1 during this stream. Yes, complex variables, exactly. Yes, e to the 2i pi is your guy. Abdullah, if you want to join the Twitch, and then if you want to hit on e to the 2i pi, here, let me shout him out. He does a lot of complex stuff. We also have a whole series of other math streamers that you can go follow. So that's all of them. Go say hi to them. They're cool. Okay. Let's do this question. Question number 4. Okay. A simple pendulum consists of a small sphere that hangs from a string with negligible mass. The top end is fixed. It's pulled to point A, so it makes an angle theta. It's released and it swings to B. The work done on the sphere by Earth between points A and B is WE. A pendulum is then taken to planet X. Planet X is the same mass as Earth, but the radius is greater. Okay, so we should just, before I even start this, let's remember how the force of gravity works. Like the big equation. So it's big G, and then it's like m1, m2 over r squared. So if you have a bigger radius planet, you have a lower force of gravity. Just solve a nonlinear OBDE. Oh dear. Okay. The spheres again point to point A, released from rest, and swung through the lowest point B. The work done here is WX. Justify why WX is less than WE. Okay. Couple ways to think about this. So, by the work energy theorem, we can say that the change in kinetic energy is equal to the net work done on an object. Okay. Now, for Earth, the change in kinetic energy is also going to be equal to the negative change in the gravitational potential energy, right? So if something starts at a height here, so like h1, and then it moves down to like h2, that change in height, that change in potential energy from gravity has to then get dumped into kinetic energy. Okay. Nice suit, bro. Thanks, bro. Appreciate you, dude. Yeah, but see, Planet X has the same mass as Planet Earth, apparently, Femvox. Okay. So, delta KE is negative delta mu G, M, right? Okay, so that's going to be equal to M, and then we're going to say G on Earth. And then that's going to be, it's like, the change in Y is negative, right? It's going down, so this is a negative change in Y. So, whatever. There's a minus here. This is change in Y, which is also negative. So it's really just equal to mge times Y. Okay. But, Planet X, the change in kinetic energy is equal to mg times the change in Y. We'll put a negative there. But G on Earth is greater than G on X, Planet X. So the change in kinetic energy for Earth is greater than the change in kinetic energy on X. So the work done is going to be greater than the work on X. I think that's what I'm just allowed to say. Kind of a long-winded answer. They went a little bit simpler here, so let's see what they did. I guess you can also say, I didn't even have to do work energy, honestly, because I could have just said the work done by gravity is the force times the distance, right? What music playlist? Oh, we're just using whatever this like lo-fi hip-hop thing is. It's kind of chill. I don't get too many copyright strikes from it. I mean, I'm a DJ. I like to play like my own music and stuff, but can't do that on live streams. I get mad. Okay. So here we go. So gravitational force would be smaller for greater radius. Good, we did do that. The sphere travels the same vertical distance. We didn't necessarily say that, but we probably should have. The amount of work done is dependent on the magnitude of the gravitational force. We did show that. Are you an engineer? I teach physics. So I'm not an engineer. I'm more of like a teacher, but not like a teacher because I don't like teach at a high school. I am teaching this quarter at UCLA though, so I mean I guess I am technically a teacher now. But I like to think of myself as more as like a educational entrepreneur. Density. Yes, well the density is definitely going to change. Because planet X and planet Earth have the same mass but different radii, so they do have to have different densities. And the changing gravitational potential energy. We talked about that. Yeah. This is, yeah, kind of more, one of the more proofy based things for sure. A lot of physics isn't a lot of proofs, but yeah, this one's kind of proofy based. Oh, I need some water. Okay, let's try to do part B here. So it says, a new pendulum is made by hanging the same sphere from a different string of negligible mass. The new string is slightly elastic, and the length of the string may increase or decrease depending on the tension applied on the string. On Earth, when the sphere is again displaced from theta, the new pendulum oscillates with a period TE. The new pendulum is taken to a different planet, planet Y. On planet Y is the same radius, but the mass is larger. Okay, so the mass is larger. We know G on Y is bigger than G on Earth. Just know that. Is again displaced from the vertical and released from rest, and it oscillates with a period TY. In a clear, coherent paragraph? What? Bro, what is this, English class? Paragraph length response that may also contain drawings explain how TY could be larger than TE, but could also be smaller than TE? Damn. This is a question, honestly, I might have even, like, if I was taking this exam, I would skip this one and go to the next. Because this already looks like difficult. Zacky Boy says, finish my CSBS, immediately jump to the channel because it's got discrete math. I feel like calculus series. Yes. Yeah, bro, what is this question, dude? Fuck out of here,
You gotta
dude.
get in the hospital now. And I just said, just shut up and let me enjoy this pain.
Yeah, I'm gonna enjoy this pain, bro. What the hell? Correct, Abdullah. I could have. Yeah, I totally could have. The reason why I use change in kinetic energy is I went to the work energy theorem, where I said the net work done on an object is proportional to the change in kinetic energy. But we could have also said because when they said the work done on the sphere, by planet X, okay, that is the work done by gravity. I was thinking you could also technically have like tension in the rope doing negative work, right? Yeah. Okay. Well, let's think about like how period relates. So, period for a pendulum doesn't matter how much the length of the string changes with the tension. Well, okay. So let's remember, right? For simple harmonic motion, where did I put that? Did I put it somewhere? Yes. Let's remember, right? Omega is equal to square root of g over L. So that means period's going to be 2 pi L over G. Is equal to 2 pi square root of L over G. Okay. And I would say GY is greater than GE. So period Y would then be less than period E. Right? Because if you got more gravity, you're dividing by a bigger number, so tension goes down. Okay. How could it change the other way, though? Ooh. If gravity on Y... Okay, but also L on Y would be greater than L on E. Okay. Do you see that? Like, so the length that the pendulum is, because it's a stretchy pendulum, the length of the pendulum could increase more, could be longer, because gravity is longer, so it stretches it out more. So then TY could be greater than TE. Yeah, let's do the elasticity. Let me see. And that's what they put down. So here's what they say. So on planet Y, right, gravitational force is larger. Thus, there's a bigger G, right? And so a bigger G means that planet Y would have a lower period. However, increased gravitational force on Y could result in the spring stretching more, which means L could go up. So now on planet Y, period could be higher. So it depends on, I guess, the stretchiness of your spring, right? Because the amount this thing stretches, right? L will be proportional to, what's that going to be? Proportional to G over K, right? Because K delta X equals mg, basically, for the force of gravity for a spring, yeah. So, yeah, okay. So as the spring gets, like, tighter, right, less stretchy, then the amount it stretches would be less. But as gravity gets bigger, then the amount it stretches gets more. So they're actually related. So actually, the key determining factor here is going to be K. Depends what K is. Okay. That's a weird one. Honestly, I might have skipped this part. And if you did, that point, that part was worth 5 points. Wow. You really didn't want to miss that. Okay. But let's see, like, what you could have done to get partial credit, because I don't know if necessarily, I think that's, if I were to guess the scoring demographics for this part, it probably would have been pretty bad. So let's see, like, all the things you could have done to get partial credit. And this is also a key thing. When you're taking this exam, if you can't answer the question, write down things you know that are true. Like, you see how we wrote that, oh, well, gravitation on Y has to be greater than gravitation on Earth, because Y has a larger mass. So if you did this, right, if we said, oh, larger mass, oh, man, I lost it 1 second. If you said, for instance, larger mass was a larger gravity, then yes, that got you a point. And then for writing down this, the period of a pendulum, we also wrote this down, even though I wasn't really sure what was going to happen. That would also get you a point. Now you already got 2 out of the 5 points. And then we could talk, I would have talked immediately about the stretch and being due to gravity. That's easy. So then these are the 2 parts that would have been maybe tricky. But you would have still gotten 3 out of 5. So, yeah, I don't know if I intuitively would have jumped to gravity stretching the length of the pendulum out more. But that's okay if you don't, you know. Just try and get as many points as you can. Okay, cool. All right. Any questions about that one before we move on to the last one? I know, we've been at it for 2 hours. Last one. And then I'll take open questions, anything on physics you guys want. All right, this should be a pretty chill one. It says it's a 17 question. 7 points, 13 minutes. Okay, here we go. At t equals 0, block A slides towards block B, which is initially at rest. A and B are 6 and 2 kilograms. The blocks collide elastically at t equals 1 second, and as a result, the magnitude of the change in kinetic energy is 9 joules. All frictional forces are negligible. Determine the speed of block B immediately after the collision. Okay. Well, this is at rest. So, B before, or so let's say like, so KE B, like initial, so many subscripts. This was equal to 0 because it was initially at rest. And then we know the change in the kinetic energy is 9 joules. So change in kinetic energy equal to 9 joules, and that's equal to kinetic energy final minus kinetic energy initial. Well, the initial kinetic energy was 0. So 9 is equal to 1/2 m v final squared, which that's a 2 kilogram block. Okay, so 9 is equal to 1/2 times 2 times v squared. Oh, this is cake. Love this. V is equal to 3 meters per second to the right, we assume. Cool. That's what they got. All right, nice. Okay, let's see what happened here. So it said the graph shown in figure 2 represents the positions x of block A, block B, and the center of mass of the 2-block system as drawn from t equals 0. Okay, so this is cool. This is the center of mass. On the circle, draw and label 3 lines to represent block A, block B, and the center of mass between 1 second and 2 seconds. So they want what happens here. Well, block B originally, right, wasn't really... What game is this? This is AP Physics 1. Most challenging game you can play. Okay, so... Here's what I know. After they collide, their velocities need to be constant, right? So... I'm not going to draw, for instance, like block A, like doing some weird changey things. It has to like do like a single line. Because after the collision, no other forces are acting on it. Oh, one thing I do know, okay, is that so momentum total is equal to mass. So this is like mass, and then this is like the center of mass. Center of mass. And then this is times, like, the center of mass velocity. And that has to be conserved. If, yeah, momentum's always conserved, right? Yeah, kinetic energy isn't. Most challenging quantum mechanics called and wants to know if Schrodinger's cat is alive or dead. Someone actually asked me this today, and whether it's a parody thing, and like... No, Schrodinger's cat being alive or dead is just showing that if you disturb us, if you try to measure a system, you perturb it. So if you try to figure out if the cat's alive or dead, you might kill the cat by like trying to figure it out. Do you know any channel where I can learn a full mechanical engineering course? I don't, but there's lots of things on YouTube. VF is equal to 3. Oh, you're so right. Oh, you're so right. Thank you, Axolotl. Yeah, we do know that block B goes at 3. Okay. So if it's traveling at 3 meters per second, then between 1 second and 2 seconds, it needs to go up to 5, right? Because 3 meters per second times 1 second is an extra 3 meters, so times 2. So you're really right. Yeah, you're so right there. Okay, cool. So that's that. Now, I believe the center of mass line has to stay the same. I believe that's always going to be constant, right? And then... this block A must be going less then, right? Block A can't speed up after hitting some shit, right? So it's got to be going less. So I think this is what we want to draw. Oh, there's an MIT course? Oh, cool. Here's a good MIT. Yeah, Zach was showing this to you. Whoever asked in my chat. But here, I'll paste it for you. I thought the Schrodinger came up with to show you that you can't use quantum ideas on a macroscopic scale. Maybe. I mean, that sounds about right. I don't know the exact history, but that sounds about right. Okay, so let's see. Let's see what they wanted for the scoring thing here. Shouldn't you calculate VF for block A? I could, but I don't think it's necessary. I just know it's going to be less. Yeah, see, so look here, Abdullah. They said the correct slope is not required. So you didn't have to figure it out. I just know it's less. But yes, okay, so you needed points for the center of mass line moving the same. That's because the center of mass times the center of mass velocity is the total momentum of the system, and that needs to stay constant. And then, right, we know B was now moving faster. This is this, and so then A has to be moving slower. Okay, cool. Oh, I see. Okay, but no, you are right, Abdullah. For the last point, to get the full points on this question, you did need to show the 1 meters per second and the 3. Okay, so we can go back and do that. That's okay. So if afterwards, so momentum before is just equal to, did they give me the initial velocity? Well, I guess I did here. So the velocity here was 2 meters per second, right? Because it travels 2 meters in 1 second. Yes. The center of mass times the center of mass velocity has to be constant. Yeah, so from this graph, though, right, we can tell that block A moved 2 meters in 1 second, so it has 2 meters per second. That's pretty cool. Little trick there. So here, so P before, you had 6 times 2 plus 2 times 0 is equal to 6 times blank plus 2 times 3, okay? So that gets me 12 is equal to 6x plus 6, which tells me x is equal to 1, all right? So that's why this has to have a slope of 1. Very cool. Okay. And then the last part, consider if the original scenario, instead of colliding elastically, the blocks collided and stuck together. Describe how the line drawn for the center of mass would change. It shouldn't. So, shouldn't change. So, center of mass line does not change. By conservation of momentum. I think that's all you have to say. Yeah, and then let's see. Yeah, okay. So for an explanation... yes. Oh, thank you, I do need to drink some water. Nice. Thank you. Water.
Is baby voice working? I hope baby voice is working. I just had to reintegrate all my OBS triggers. Okay, cool. Yeah, so you can say that the center of mass line does not change. And again, that's because the total momentum of a system, guys, is the center of mass value times the velocity of
that center of mass. So there's a way to calculate like kind of how like the center of mass, like here, like the center of mass is like closer to here, right? Because it's weighted more heavily towards the 2. But then when they collide, now this thing is gonna be like moving away. But the velocity of the center of mass also like moves at the same rate it was here. It's kind of a wild concept, honestly, but I need like a better visualization for that, but let's see if I can find one real quick. I wanted something that looks cooler. If you want to submit, so that's all. So yeah, we've just done, that is all the FRQ for the AP Physics 1 exam. So we're done doing that. Congrats. Thank you everyone who stuck around to like go through it. I hope that's helped you. What I will do is, I'll post this PDF of everything we went through. Also, a recording of this will be available. And I'll tell Dan or whatnot to maybe email it out to you guys. But also you can check on the YouTube. I think on YouTube it saves the recording as well. But if you want this PDF, I'll also post it in my Discord. You can join our Discord. Again, if you go to actualdiscord.com/submit, which is the link here, you see at the bottom, you can click here to say join our Discord. That'll join the Discord as well. So, could I do a fluids exercise? I could, for sure. Do you guys want me to do like an example fluids question? Yeah, of course. You're very welcome, Zach Boy. Yeah, so now what I'll do, like for maybe the next like half hour, is I'll answer any other questions about AP Physics if you want. So let's do like a fluids question. Okay. Apparently a lot of this came from like AP Physics 2. Let me see. One sec. One place to get this. I'll post some links for some people. Here we go. Continue. Okay. Let's pull these in. So here is some fluid practice questions. So what happened with AP Physics 1 is they pulled fluids from AP Physics 2. So all the AP Physics 2 questions on fluids are still kind of valid for AP Physics 1. So here, I'm going to dump some links. Those should work as well. But let's pull some questions in. And then I need to see what equation did they. I don't know if they post the equation sheet of it. Yeah, of course. Yeah, please. Yeah, feel free to come on by if you ever have any more questions about stuff. Like even if you get to college and I don't know if Vector Cal is giving you trouble. Happy to help you out. Okay, so let's see here. Here's some example fluid questions here. It says two substances, mercury with a density of 13,600 kilograms per meters cubed, and alcohol with a much lower density, 0.8, are selected for an experiment. If the experiment requires equal masses for each liquid, what is the ratio of the volumes? Okay, so this is pretty cool. So the key thing you need to remember here, guys, right, is that density is equal to mass divided by volume. Okay. And so if I'm rearranging this equation, I can say that mass 1 is equal to density 1 times volume 1. And what they want is they want things to have equal masses. So we could also say that mass 2 is equal to density 2 times volume 2. But mass 1 equals mass 2. So if you set this equal to this, you're going to get that like D1 V1 equals D2 V2. And this maybe should remind you of in chemistry, right? You ever do like dilutions and stuff? This is kind of how it works. It's like molarity times volume. Okay, it says, what is the ratio of the volume to mercury? Volume of, let's say alcohol to mercury. So let's say that mercury, so let's say alcohol equals 1 and mercury equals 2. Okay? So I want to know what is V1 over V2, right? That's the ratio of alcohol volume to mercury volume, right? Well, looking here, right? If I wanted to get V1 over V2, I could just divide this, and then I could divide the other side by D1. So watch. So you can take this over, divide by V2, and then you can take this over and divide by D1. And so what you end up getting is that V1 over V2 is equal to D2 over D1. Also, yeah, like density and volume are inversely proportional to each other for the same mass. So if this is constant, this goes up, this has to go down. So you can kind of see this here. So I need the density of mercury. Well, so alcohol volume to mercury volume. And then it's going to be this seems like a really high number, by the way. What? 13,600? I don't know if maybe this question's wrong. One sec. Okay. It's missing a yeah, it's 13.6. I was like, bro, that's really fucking heavy. Okay, 13.6. Thank you. Yeah, I was like, bro, what? Okay. So, obviously, there are some problems already with questions here. Okay. So, 2 is mercury. So, 13.6 divided by 0.8. Okay. Which, let's see if we can get like a nice number for that. So, wait. No, it's kilogram meters cubed, kilogram meter cubed. I think they made a mistake. But this comes out to being 17. So the answer should have been E, 17 to 1. But a meter cubed is 1,000. Yeah. Right, so you're right, Abdullah. Abdullah, that was a gram. That was a gram per centimeter cubed. Yeah. So yeah. The key thing here, axolotl, is this should have been 13.6. This is wrong. It's not 13,600. That's way too big. Okay, yeah, and the correct answer was E. Okay. So let's look at 2. So it says a perpendicular force is applied to a certain area and produces a pressure P. If the same force is applied to twice the bigger area, what will the new pressure be? Okay. So the equation you need to remember for this is that pressure is equal to force over area. Okay. So what we can say is that F1 is equal to P1 A1. Okay. And then so another force, F2, would equal to P2 A2. So we have the same forces but different areas. So same forces, so I can set these equal to each other. P1 A1 equals P2 A2. And we're looking for eventually the the new pressure on something. So the new area is twice as big. So A2 is equal to twice as big as A1. And so then I get that P1 A1 is equal to P2 times 2A1. You can cancel out the A1s. And so you get that P2 is equal to P1 over 2. So the new pressure will be half of what it used to be. And that should make sense from here as well, guys, right? Pressure is equal to force over area. So if you double the area, you should be having the amount of force, or having the amount of pressure, sorry. If you have the same force. Smash. Yeah. Okay, so that answer is D, which is also correct. Okay, let's get to something a little bit harder. Yeah, let's do this. This is a good one. Oh, is that the issue? It should have been 800. Yeah, because 0.8 also seems weird. Okay, so they messed up royally. So ignore this question. I'm gonna tell them like this is a bad question. Let's try to do this one. This is kind of a cool one here. It says a hydraulic lift is used to lift a car, a small piston of radius 5 centimeters and a large piston of radius 50 centimeters. The driver applies a force of 88 newtons to the small piston. What is the weight of the car the large piston can support? Yeah, they made a lot of mistakes in that one. Okay, this is a cool one. What grade are the questions from? This is from AP Physics 2, is what this is. Okay. So what we know from Pascal's principle, right, is that the pressure applied in a fluid has to be constant everywhere. Good. Exactly. Right? So the pressure here, we say like P2 has to equal the pressure here, P1. So old AP Physics 2, they took the fluid section from AP Physics 2 and they put it into AP Physics 1. AP Physics 2 is like waves and like other like weird topics. Okay, and so we remember, right, that P is equal to F over A. So P1 is equal to F1 over A1. And here P2 is equal to F2 over A2. But since P1 equals P2, that means that F1 over A1 has to equal F2 over A2. So let's see. This driver applies a force of 88 newtons. So I'm going to say 88 and a radius of 5 centimeters. So the area, we assume the piston is circular, right? This is going to be pi times 0.05 squared. That's going to equal some new force that is going to be supported by the car over an even bigger area, which is going to be P, which is pi times 0.5 squared. Exactly, Jeff. Yeah. So now we're just solving. So algebra-wise, this is kind of cool, right? Because this goes away. And then the cool thing you can notice here... Yeah, watch this. Watch. This is actually really cool. You actually don't even need a calculator for this. If I multiply this up top, guys, this is going to be 0.5. What grade would you take this in school? High school. This would be like 10th or 11th, maybe 12th. So, yeah, 11th or 12th. I can combine this as a single fraction under an exponent. So this is 0.5 over 0.05 squared. And 0.5 over 0.05 is the same thing as 10. You see how like this is only like 1 0 away from it? It's like how many 0.05s can I put into a 0.5? Well, I can put 10 of them. So now this is 88 times 10 squared. So this is 88 times 100, which is going to be 8,880 newtons. So this should have been answer choice C. Yeah. Nice. Okay. I want one with like buoyancy. Okay, I like this. Yeah, let's do this one. Oh, website to keep sharp. So yeah, if you want, one sec, let me get you the website. If we go to, one sec, it's www.actual, no. Hold on. Would you rather have a black son or a transgender daughter? God damn it. The trolls we get from YouTube sometimes. Okay, here we go. One sec. I wanted to give you the link. Where's my YouTube links? Here we go. There we go. That website should have a bunch of like practice physics questions on it if you want to stay sharp. So actually, if we click on this one, let's see. I can probably let's pull up like the fluids section because there's 66 homework questions here. You can go through fluids. Abdullah says, "Can you look at my previous message?" Sorry, let me check it out. Sorry, there's a lot of stuff happening in the chat, Abdullah. Oh, okay. I see, Abdullah. I got you, dude. Yeah, the one for mercury was okay. The one for alcohol was wrong. All right, so let's see some questions here. Let's get like a fun one. I want one with buoyancy on it. Yeah, here we go. This is a good one. Oh, wait, Dunkles is like posting a question. If you post a screenshot of that question, it could probably help. All right, let me pull it in for you. All right, where is it? Okay. Yeah, if you try, yeah, so here, if you go to this website right here, actualdiscord.com/submit, which is down there, and if you type in your username, and you can upload a screenshot, like, because I'm sure there's a diagram or something, and if you hit upload, I should see it here. Okay, cool. Yeah. See if you can paste it, and then I'll pull it in. Yeah, not this one. Okay, this is a good one with buoyancy. So it says you can use Archimedes' principle to calculate the density of fluid as well as that of a solid. Suppose a chunk of iron with a mass of 390 grams in air is found to have an apparent weight of 350.5 grams when completely submerged in an unknown liquid. What is the fluid's density? Okay. So, if we have something here, which is 0.39 kilograms, we can figure out what the mass of that is, right? So, that's just going to be equal to mg, right? Well, wait. No. Okay. We're just going to leave that like that. Okay. When it is completely submerged, okay, it's now going to have an apparent mass of 350.5. Yeah, I'm good with algebra. You're good. Okay. So when it's submerged, you're going to have buoyant force, which is going to be equal to rho of the fluid times g times the volume that's displaced, right? So, one sec. I'm pretty sure that's Archimedes. I think it's rho GV. Yeah, rho GV. Okay, cool. Awesome. But then it also has the force of gravity pulling down, which is equal to the mass of this thing, 0.39 times g. Okay? So then the net force, right? So we can say like F net on this object is equal to rho GV Ooh. And I think this rho GV, if it has an apparent mass, right? That means that it feels like it's a opposing this is like kind of like the normal force. If you guys remember this from like earlier kinematics, right? If you're standing on something, the normal force is like how heavy you feel. And I believe this is kind of like the normal force. So I think this is just rho GV is equal to 0.35, 0.5 G. Right? Yeah, let's see what that is. But I don't know V. Wait, how do you do this one? The flu stuff is interesting for sure. Oh, do I have to look up the density of iron? That's cheating. I was looking, I'm like, wait, can I get this without the density of iron? Oh, man. Oh. And then density needs to be in like kilograms per meter cubed. Yeah, which is 7860. Oh, wow. Okay. I see. Wait, one sec. I think I can get this. So... Wait, 7860. Is equal to 0.390 over the volume. So volume is equal to 0.390 over 7860. Okay, cool. So then that goes into this. The G's cancel. So then rho is equal to 0.350 divided by 0.390 times 7860. Yeah. Well, let's see. So then what is that? 0.350 divided by 0.390. So that's kilograms per meter cubed. Which then I believe is 0.7 grams per centimeter cubed. So I think the answer is E. Sorry, there it is. We can actually check that. Let's see. Well, is that right? Wait. Oh, so it's not that. One sec. Ah, so it's 0.79. Okay. Yeah, okay. Here, let's do this one. I want to do this one. This is a good one. Someone submitted this from our thing. Okay. When the atmospheric pressure is 1 atmosphere, a water fountain ejects a stream of water that rises to a height of 4.10 meters. There is a 1 centimeter radius pipe that leads from a pressurized tank to the opening that ejects the water. The water has a density, cool, of 1. Calculate the height of the water if the fountain were operational while the eye of a hurricane passed. Assume that the atmospheric pressure in the eye is 0.875 atmospheres. So less than 1 atmosphere, and the tank's pressure remains the same. Oh, okay. Did you chat GPT this one, or did you solve it? You actually solved this? Okay, cool. All right. The weight of the water increases linearly with the height. Okay, so we need to relate what the velocity of the water going out is, right? Because we know that if something has an initial velocity, right, 1/2 mv squared, when it gets to its maximum height, that's going to be equal to mgh. So that tells me that, what is that? H is equal to v squared over 2g, right? So I need to figure out, yes, sure. You cannot be banned. It's okay. Okay. So by Bernoulli's equation, which, let's pull it up. L roses, yeah. Mm-hmm. Pressure. He just said plug in Bernoulli. No, I want to understand it. No, this is. I need like a picture of like what's happening here. Well, okay. They say that the tank's pressure remains the same, right? So you can think about like you have the tank and you have you have the opening. And then I assume it shoots straight up, right? Yeah, let's do this. Okay, watch. So here you have the pressure of the tank. And then velocity is going to go straight up. So the pressure in the tank stays the same. But then here, this is P atmosphere. Okay? Yeah, no, it's okay. It's okay. Interesting how this is going to come out to be the same, right? If I plug this into here, yeah. See how you're going to get rho g v squared over 2g? This is going to cancel. And so you're literally going to get 1/2 rho v squared again. I see. I see. Because like there's a velocity of the fluid coming out of here, and then there's the velocity of the fluid at the top when it's 0. Yeah. Okay. A1V1 equals A2V2? Okay, let's think about like when it's here and when it's here for like regular atmosphere. Okay? So, and then let's call this height equal to 0. Okay? So, when it's in the tank, you just have the pressure of the tank plus 1/2 rho v1 squared plus 0. And that has to equal the same thing when it's up here, which is now just going to be the pressure of the atmosphere plus 0 velocity. It's not moving anymore. But then this is going to be plus rho g h2. Okay. We don't know what the pressure in the tank is. All right, so this is regular atmosphere. So in this case, pressure in the atmosphere is equal to 1. Or do I have to put things in pascals? I think I have to put things in pascals. Or here, let's call this like P1. Or I'm going to call this like P regular. And then we have the same case here, right? P tank plus 1/2 rho v1 squared plus 0 is equal to P hurricane. Nice. Plus 0 plus rho g h. And here, I know that this rises to 4.1, right? So we're trying to solve for this new one. We're clearly relativistic. Oh, no. Okay. I don't think I care anything about the 1 centimeter shit. I don't think I care anything about that. What's up, 1K? Okay, so let's just solve. Let's solve this bitch, right? So I feel like this all just cancels out, right? If I subtract the two. So then I have 0 is equal to P regular minus P of the hurricane plus rho G, and then it's 4.1 minus H2. Right? So that's the same thing as P of the hurricane minus P regular is equal to rho G 4.2 minus H2. Hurricane pressure was 0.85. Whatever. 0.875. So this is going to be 0.875 of 101.3 times 10 to the 3. Right? Minus 101.3 times 10 to the 3 to get in pascals. And then the density of the water is just 1. 9.8, right? Is there any way to stream full screen? Yes, you can watch us on Twitch. Twitch, there's a full horizontal one if you want to see. So again, go to that website, actualdiscord.com/submit, and then click watch on Twitch. That has the full horizontal. Okay. And then this is going to be 4.2 minus H2. I think we can solve this. I'm so sorry I called you fatty. What? I mean, I have gained some weight. All right. Let's see if we can get this. I think I got this. I just got to trust. It's been a while since I've done fluids, honestly. And it's pretty mean that they just lumped it on for you guys, like, all of a sudden. Like, AP Physics 1 already has, like, really abysmal passing rates on it. Like, why would they do this to you? But I believe in you guys. It's also 10 to 15%. Yeah, and also they have like no like previous. I guess again the AP Physics 2 technically has it. Okay, so that divided by 9.8. That's gonna be really fucking big.
Nice.
Oh. But the density is 1 times 10 to the 3. My bad. This is not 1. This is 1,000. A container of water cross-sectional area, this, has a piston sitting on top. There's a spout located 0.15 meters from the bottom of the tank open to the atmosphere, and a stream of water exit the spouts. The cross-sectional area of the spout is this. What is the velocity of the water as it leaves the spout? The spout. How do you watch this on Twitch? You just click on the Twitch link and it'll do it. Okay. So I think this is going to exert a pressure, right, guys? There's going to be a pressure from this. So let's remember that pressure is equal to force over area. So that's going to equal the 20 kilograms times 9.8. So that's the gravity, right, of the piston. Divided by the area, which is 0.179. Oh, I'll give you the link, dude. It's okay. There should be a link there if you just click on it. There you go. Okay. So let's get a number for this. So I get 20 times 9.8 divided by 0.179. Cool. So that's going to equal to 1095. Let's just say it's equal to 1095. And I think that's pascals. That's what we call that. Okay, and they want to know how fast the water is coming out here. That is true. The pressure will be the same. I think it depends on the velocity, though, Jeff. Okay, so let's try to do... If I use... let me try to use Bernoulli's equation here. I think I want to. Because I believe here... we don't need to account for atmospheric pressure because it's sealed at the top, right? I think if we're going to look at, like, for instance, it here and it here, right? So let's see what that difference is, right? So P1 would be 1095 pascals. Not very heavy. 20 times 9.8. 200. Okay. But then, do we assume that the... Yes, exactly. There is atmospheric resistance. There is atmospheric pressure when it leaves. My question here is, how do I know the velocity of the water dropping here?
Nice.
Or do I assume it's 0? Yeah, what's up, Harvell? I see you. I think maybe we can assume it's 0. Let's just assume it's 0. And then plus rho, that's 1,000 times 9.8 times the height. And so the height of that's going to be 0.5. Okay. And now this has to equal 101.3 times 10 to the 3 plus 1/2 rho v2 squared plus rho g, and now the height 2 is at 0.15. Ooh, I think there's a continuity question. Yes. Okay. What is it? What is it? Fluid continuity equation. What is it? Yes. A1V1 equals A2V2. I think you said that earlier. Axolotl, right? Right. Okay. So so A1V1 equals A2V2. Gosh, good. AV is constant. Yeah, I agree. Yeah, we love that. Okay, cool. So, yeah, actually, so let's move this over. So this term won't be 0. This will be plus 1/2 rho. And then V1, right, is equal to A2 over A1 V2. So this is going to be Bernoulli flows is only valid for steady flows when the tank area is much larger than the exit area. Well, I feel like that is pretty big. What? We got 7 times 10 to the minus 4 compared to like 1 times 10 to the minus 1, like 2 times 10 to the minus 1. That's pretty big, right? Yes. Yeah. Yeah, big shout out. We got a bunch of people that are awesome. And however, if you wanna go follow all these people. They're also really great people. Let me see. Oh, we have to add in atmospheric pressure here. Sorry. This is not isolated. Oh, wow. Okay, one sec. A piston sits on top of the water. Okay, but this is open to atmosphere. Oh, man. Sorry. This also is 101.3 times 10 to the 3. So I thought, okay, this diagram's misleading. I thought this was closed off. This is not closed off. This is open. So you have the force of the atmosphere plus the force of the piston. Newcomer, here's a problem. It's like a Bernoulli question. Yeah. Yeah, so here's the cool thing. So when you solve for this, if we added in this is 101.3 times 10 to the 3. This will kill this, whatever. You end up getting V2 is equal to 3. Which, I don't know. Because that looks like such a nice number, I'm pretty sure it's right. So let's try it. Let's put in 3 meters per second. Wow, it's correct. Yeah, very cool. Oh, that one works. Oh, very cool. I was a little, yeah, I didn't know that. I thought the piston was inside like something that was closed, but it's not. Piston is open as well. That's weird. Okay, whatever. Munchie says, asking because I'm in college, and you can ask about anything, dude. Yeah, so this stream specifically was just for AP Physics 1 students who have their exam tomorrow. Good luck, by the way. But we stream 3 times a week, Monday, Tuesday, Wednesday, here on YouTube and on Twitch. And you can submit whatever. You can ask whatever question, math or science related, and I will try my best to help you out with it. So we do everything from, yeah, here we go, like Gaussian integrals. Yeah, I mean, this is also like valid technically. Yeah. What are these problems from? So these problems that I've been working on with the AP Physics 1 students come from the website Kudu. So if you want to like get free access to some AP Physics 1 questions, I'll post the link here in the chat. So what we did is we went into the fluids section of the course, which has 66 practice questions that you can check out. And we were just doing one of these, which was involving like a tank and water and like things falling out. Yeah. So a bunch of fluids questions here. This is the one we were doing. That was pretty cool. But yeah, I actually have to go run and teach another student. We've been streaming for almost 3 hours now. Wow. Super cool. So I hope this was helpful for you AP Physics 1 students. Again, best of luck with your exam tomorrow. I really hope it goes well. Please feel free to use those resources if you want to do some more practice questions, but also don't stress yourself out too much tonight. The best thing you can do for yourself is don't be like cramming and losing sleep. The best thing you want to do is get a good night's rest and be calm and collected and like do your best on the exam. I'm glad you came across our stream, dude. Yeah, awesome. But yeah, so if you found us here through AP Physics 1, like, awesome, welcome. Feel free to join. There's a Discord link there. I'll post it also in the YouTube if you want to get more free help with what we do here. But also, we have a calendar because I'm not the only person that does this. Actual Goat. Yeah, dude. Thanks, Axolotl. Yeah, Axolotl, if you ever need help with any of your other classes, anything, you know, math, science, whatever related, we have a calendar here showing when we stream. I usually do Monday, Tuesday, Wednesday, around this time. And you can come on by and ask anything math or science related, and we'll do it. I've done everything up to, like, Diffie-Q, differential, you know, real analysis, whatever, to as basic as, you know, just algebra and geometry. I can definitely teach you fractions. I've taught a lot of people fractions. You're taking BC Calc and AP2 next year? Awesome. Yeah, cool. If you're doing that, please, you know, like, subscribe, all that fun stuff so that you get notifications when we go live, and so you can hop on and ask questions if you want. Otherwise, you can also join our Discord, and that's a cool way to keep in touch with us. I'll think about streaming weekends. My weekends are pretty busy so far, but according to our calendar, Zach does do math help on Saturday mornings. So if you want to get help on the weekends, Saturday, Zach can help you out here. And then Talos actually does a introductory calculus course on Sundays. And yeah, we have some other like fun stuff going on. So check them all out. Okay, with that, I hope this was helpful for you guys. Best of luck on the exam. I really hope it goes well. And we will see you guys if you're coming back for normal tutoring. Our next stream is going to be Monday. That will be 3 p.m. Pacific, 4 p.m. Mountain, 5 p.m. Central, 6 p.m. Eastern. Same channel, same place, just slightly earlier time. And for those of you that are on Twitch with us, we're going to go raid another person. This is how like Twitch works. In my experience, there's no such thing as luck. I say there's good skill. I say you create your own luck, right? All right, let's see. Who are we following? We can go raid. Merryweather's doing more funny things. Someone's building a... Okay. Let's go say hi to Nerduino. Let's go say hi to Nerduino. Nerduino's doing some cool stuff with astronomy. There are a lot of really cool streamers here on Twitch, and we love to be a part of the whole gang here. So spread knowledge, have fun. Okay. Best of luck on the exam. Enjoy the rest of your weekend. We will see you on Monday. Peace.